fifth day of ATAL AICT Faculty Development Program on Machine Learning for
Hello, good evening, all. Uh, yeah, we are at the last day of our online FTP session. fourth day, and we have our distinguished speaker Abhijit here from here IIT Madras. He's actually the research scholar of Dr. Sarith in Applied Mechanics Department. So I invite Vinita, a research scholar, to formally invite and introduce Abhijit. Vinita, are you there?
Yes, sir.
Yeah.
Good evening, all. Handling the session. Mr. Abhijit A is a senior research fellow at IIT Madras, Chennai, under the guidance of Dr. Sarith P. Sathian. He received his B.Tech in Mechanical Engineering from CUSAT and his M.Tech in Thermal Power Engineering from MG University, Kerala. And he is doing his PhD in Computational Quantum Chemistry at IIT Madras. Along with having more than 5 years of experience in conducting interdisciplinary research, he has also held the position of Chief Technology Architect at Quantica Computer Care, Chennai, and has taught the postgraduate course High Performance Computing at IIT Madras. His current interests include predictive descriptive analytics, CNN, GIN, NLP, time series forecasting, and so on. He is highly passionate about cloud architecture, data driven automation, and full stack system design of data intensive applications. Mr. Abhijit A has several publications in various national, international journals and conferences to his credit. He is also the recipient of University First Rank in M.Tech Thermal Power Engineering from MG University, Kerala. His recent research focuses on implementing and porting of simulation environment and evolving native machine learning algorithms for the study of electronic structure calculations. With immense pleasure, I welcome you, sir.
Thank you very much, Vinita. I hope I'm audible.
Yes, sir.
Yeah,
Okay.
Abhijit, you are audible.
Yeah, thank you very much. So, uh, okay, good evening, ladies and gentlemen. Uh, thank you for joining me on this Saturday evening. Uh, so, just before getting started, I just want to say a few words. So today here I'm presenting on behalf of my professor, Dr. Sarith P. Sathian. So he was supposed to be here doing this presentation, but because of some unfortunate personal reasons, he is unable to make it. So I will try to make it up for him and try the level best to deliver what is expected of me. And I would like to thank Dr. Shailesh and other coordinators for making this possible and giving this opportunity. So, shall we get started, sir? I hope
Yes,
everyone is here.
sure, Abhijit.
Okay, great. So, let me share my screen. I have a presentation made. So, this was on short notice. So, I just made this presentation, cooked it up in just 2 days. So, I hope you forgive if there are any mistakes. So I hope my screen is visible. Can anyone give a feedback? Is everything fine? Is it visible?
Yes, sir, perfect.
Okay, great. I'm just turning off my video because in case if the network goes down, there will be some bandwidth shortage. Okay, great. So, so the topic of today's talk was given to me. It's basically machine learning and artificial intelligence in interdisciplinary research, challenges and future opportunities. So, I would like to make a generalized presentation rather than focusing on what we have done in our lab. I just made it pretty generic because I know the current audience that we have right here could be faculty from different modalities in mechanical engineering. So I believe there could be a piece of cake for everyone attending the presentation. So here are the topics that I'm planning to cover in today's presentation. So first of all, I will give a big picture, a bird's eye view of what is happening in data science domain and its application in industry as well as in multiple research disciplines. Then we will narrow down our discussion to AI/ML in applied mechanical engineering as well as mechanical engineering related interdisciplinary research topics. Then we will discuss in general about the modeling of dynamical systems and how AI has adopted into just about every arena of modeling of dynamical systems. And then to present the exact scenario of what exactly is going on in the frontiers of research and the current cutting edge topics, we will take 4 different case studies from different domains of mechanical engineering. So I have chosen like fluid mechanics, manufacturing, material science, and nanoscale transport. So nanoscale transport is something that we do in our lab. So that is the place where I'm planning to discuss about what is happening currently in our lab, because we only pivoted to this area very recently, and so far we have been focused on other classical and conventional techniques. But and our presentations are our publications are also not yet through. Much publications are not there in terms of machine learning based techniques. So I will confine my discussion there into what is done in our lab. So rest of the part I will try to picture what is happening around the clock, and then I'm planning, if time permits, I will do a hands-on demo of. Again, I didn't get enough time to prepare for the hands-on demo, so what I will do is I will just show you a simple demo of how to approach if you are planning to do or planning to enter into the topic of ML-based research, and I will show you what are the resources available and how you can go about it. Okay. So let me just put the context of the presentation, like what to be expected and what not. So we will be primarily focusing on how AI/ML is adopted in mechanical engineering. So this is of pivotal importance in my perspective at least, because nowadays, as we know, mechanical engineering has is an age-old discipline, but currently we are facing this scenario where mechanical engineers are finding it very hard to find positions in industries, and most of the research in mechanical engineering has diverted into sort of interdisciplinary branches. So nothing related to pure mechanical engineering is nowhere to be seen anywhere around us. AI/ML has a very crucial role. In fact, it's much more closely tied up than anyone would anticipate to mechanical engineering. I'll make it clear during the course of the presentation. Then we will be having specific case studies from 4 different mechanical engineering domain where we have successfully applied AI/ML in different research problems. Then we will take a look at the current challenges. What are we facing in the cutting edge research on different fronts, and the opportunities that we have if we are trying to pursue an interdisciplinary research. And what this talk is not, we are not going to deep dive into any AI/ML algorithms because we don't have enough time for that, but you can consult with me anytime if you want to pursue further or understand in deep about any of the algorithms that I'm discussing here today. We will not be discussing the business context, though I will be brushing upon it in the initial part of the presentation a little bit, but not specific. Then we will, there is a lot of talk in both in the industry and the academic arena about the moral and ethical dimensions of AI/ML applications. So those things are also not covered in this presentation, but that's also something which is going on nowadays. You can take a look about it from different research journals. So how I am planning to deliver this? So this presentation I am trying to put it like this. So first of all, I will try to address the curiosity of a person who is actually trying to enter the field of interdisciplinary research by a domain expertise in mechanical engineering, and some basic understanding of artificial intelligence and machine learning. I will try to put myself in the shoes of that person and try to answer most of the questions that you might have in mind. So please feel free to unmute and ask me if you feel anything needs to be explained further. All right. So first of all, we can start by addressing this question: why AIML is relevant? So, like I already pointed out, it's actually found in a majority of applications all around us. Even if you go to a movie theater, from the selection of choice of movies when you're trying to book it in an app, to the selection of food that is happening if you're in a metropolitan city, how the food is chosen based on seasons when you're on a movie break, or when you post a review for the movie, how that is analyzed. Everything, knowingly or unknowingly, that we touch upon in our daily lives is one way or the other now connected to some form of machine learning and artificial intelligence applications. So AI is currently successfully commercially adopted in a lot of industries. I have listed down a few which I thought is mostly relevant. So in healthcare, there is a lot of research going on, especially in precision medicine, wearable sensing, and drug design. So we have some work going on in our lab about targeted drug deliveries and cell design. I will not be touching upon all these topics because we have limited time. Then it's applied in logistics, in delivery systems, automation, vehicles, navigation, etc. Then in robotics, in education, manufacturing, and in banking for obviously for recommendation systems and all that. So this is like a generic picture. Like there are a lot more industries. So here is a report from the McKinsey and Company. It's a top management consulting firm in the world. So if you take a look at this statistics, so this is given by a research report published by them in 2021. So they have actually given the comparative incremental value of AI in different industries compared to the traditional analytical techniques. So this McKinsey reports are one place where you can find if you're interested in what's going on in industry and currently what. I'm sorry, I'm hearing some noise. Someone has unmuted.
Excuse me, sir.
Yes.
Sir, sorry to disturb you, but the slides
No
are
problem. Yes.
slightly blurred. So,
Oh, really?
yeah.
Okay. I hope it is only this part, which could be maybe because the letters are very small.
No, sir, no.
If
It is
you-
blurred.
No,
Previous slides are
even
also blurred.
even the previous slides were
Oh, the
blurred.
previous slides were blurred. Oh, this one is also blurred.
Yep, sir.
Oh, I'm not sure why because could we the- I mean it definitely has something to do with Google Meet. I'm not sure. Uh, So, is there anything we can do about it? I'm not sure about this. Dr. Shailesh, can we do something about this? I mean, do you have any idea? Is it better now?
No, sir.
So nothing is visible. Is it like that? Or?
Big picture can be read.
All right. Oh my God. Okay. Let me try changing the network. I'm not sure. Is it better now? Can anyone
Yeah.
count? Is it visible? How is it?
Abhijit, it's blurred.
Sir, your voice is breaking. I can't hear you. Can you repeat that? Yes.
Actually, the slides are still blurred.
Sorry, sir. Uh, uh,
Hello, can you
Hello?
hear me,
Yes,
Abhijit?
sir. Yes, sir. Please tell me.
Yeah, actually, the slides are visible but blurred.
Yes. Oh, all right. Okay. So I'm not sure why this is happening. Okay, let me take it. Uh, Sir, is it visible here right now?
Now also it's blurred.
It is blurred. I don't know exactly what is the reason. I believe it has something to do with
I
the
think,
connectivity.
can you adjust your resolution, screen resolution?
Uh, all right. No, but I don't believe it has something to do with the screen resolution. So you can do that.
So you can try sharing the tab rather than the entire screen.
I forgot where this is actually. Screen. Yes. So do you want me to switch to say? So what would you suggest? Maybe a lower resolution or
Yeah, can you put it in the maximum resolution
the
setting?
maximum resolution? Okay, it's already in the maximum resolution. That's what I'm asking.
Oh,
Yeah. No, no, it has nothing to do with the resolution uh, because I'm seeing it very clearly over here. I don't know what is the reason. Maybe I can share this presentation with you guys, and you can actually view it offline or something.
Sir, can you try sharing the tab rather than the entire screen?
This is not a tab. Actually, I opened it in a different because this has some movies embedded in this PDF. So I just opened it in a different PDF viewer. So it's not open from any browser. I could not. I'm not sure if it will play it in a browser. So I'll do one thing. I can share the presentation with you. So you can open the presentation by yourself and just go through that. I believe there is a. So can I email you the presentation? Can you share it with the participants so that they can view it offline?
hello.
Sir, can I share
Please
the
share the.
presentation? Oh,
Yes, share with the same mail ID you got the invitation.
okay, all right, okay,
They will share it with the participants.
all right.
Yeah.
So give me a second.
Please receive that slides and share it with the participants.
All right, all right.
Hello, Anjali, you there?
Yes, sir.
Anjali, please receive the slides and share it with the participants.
Sure.
Uh, It has some embedded video, so the file size will be a little big. You might have to download it directly from the drive. All right. Sir, shall I continue with the presentation? Anyway, you will receive this presentation, so
Sure, Abhijit. Yeah. You
Okay.
can continue. Meantime, they will get it.
all right, okay. All right. So, I was talking about the analytics presented by McKinsey and Company. So this research is done by McKinsey Global Institute of Analysis, and they came up. Every year they publish this report. And if you need to know about what's going on in the industry, where all MI is applied, so these guys have a huge survey. They've done it extensively and very well sampled. And you can get a holistic picture of exactly what is going on and what will be the future of this industry, what is the value proposition in next 3 years. So we can clearly see here, I don't know how much this is visible, but if you take a look at all these plots, here we have few circles. So the light colored ones, which are the inner circles, actually represent the value addition in $1 trillion provided by AI, compared to the larger circles, which actually represent the total value addition of the company. So it adds up to 9.5 to 15.4 trillion if you compute the value in all these different domains like marketing, supply chain, risk, finance, HR, IT services, everything added up. And AI and ML alone accounts for about 3.5 trillion to 5.8 trillion of value addition. So that's the role of AI in the current market. And as you can see, almost 70% of the companies actually have reported and improved performance over that provided by the traditional analytical techniques. So if you need more information about this, you can go to the McKinsey and Company website. We can freely download the report and go through it. They have a lot more details and interesting statistics out there. All right. So keeping apart all this hype about the artificial intelligence and machine learning, there are also some challenges associated with it. Each domain has its own specific challenges. When it comes to research and interdisciplinary research, there are challenges associated with that as well. But here I wanted to address, so before getting and diving deep into that, I wanted to address some domain agnostic, some generic challenges that we face today. So this includes decision explainability. Just give me a second. I have sent the presentation. So hope it will be shared with you soon. Okay. So the primary challenge is decision explainability. So in most cases where we apply AI/ML models, one primary challenge that we go through is how to interpret and explain the models. It's because these algorithms mostly study all the nonlinearities within the models that we make, and that is pretty much like a black box. We just give the input and we obtain the output by training the model from the data. So there is no scope of explainability in such scenarios. So that comes out to be a problem in most cases because we don't know whether it leads to different sort of problems like the ones I'm planning to present here. So one is dataset bias transparency. So recently there was this report by applications that are deployed in the human resource sector. So they were reporting that the AI applications were actually being gender biased and race biased by race and ethnicity and everything. So there was a huge debate going on whether we should actually rely upon such applications. Then there are criterions of regulatory agencies to ensure responsibilities. Like it's very difficult for regulatory agencies to come up with some criteria, or in most cases also the standardization agencies like ISO also comes up with this kind of difficulties, primarily because of the decision explainability, and most of these models are actually subjective to the data. I mean the performance of the model as well as the decisions made by the model are actually highly subjective to the training data. So it's highly difficult to make standards out of that. Then there is threat to security. This is mostly in IT domain as well as in other domains which, as well, where there is threat of data security. All right. So now that we have set the context and we explained about the holistic picture of AI/ML, let's now come to the topic of today's discussion, which is AI/ML in mechanical engineering. So why machine learning or artificial intelligence is an inevitable skill for a mechanical engineer or a future workforce which is having a domain expertise in mechanical engineering. So I'm quite sure you all might have heard of this buzzword Industry 4.0 that everyone is talking about it nowadays. So it's called the fourth industrial revolution, where this manufacturing sector is moving towards something called as smart manufacturing. I have provided some citations along with this presentation, where if you are interested, you can go further and read about it. So there is a lot of AI/ML applied AI/ML scenarios in case of all these smart manufacturing sector. Then there is material properties prediction. It's also something which someone with a domain expertise in mechanical engineering can effectively make use of using machine learning. Then there is autonomous driving. It's actually an application of reinforcement learning, which is like even without training the algorithms are actually trained to train itself. So it's also an emerging field. There is no commercial applications so far. Then there is additive manufacturing, which is again the new normal in the manufacturing sector, where you can print materials from CAD models layer by layer. There also in multiple scenarios we have applications of AI, and we will take a look at these things when we come to the case studies. Then there is atomistic modeling of materials. That is AI plays a very critical role in the modeling of materials nowadays by accelerating the time that we need to simulate different materials. We again look into details of these things. Then there are this turbulence control problems, which are very crucial in the fluid mechanics domain. We'll be discussing all these things in the case studies in detail. So here are some news articles which I found quite fascinating from the industry. So recently, again from McKinsey & Company, they reported that there is a reduction of 50% error in forecasting supply chain by use of AI/ML algorithms. Also, there is this Forbes report where they have found an increase in defect detection rates of 90% when applying AI/ML algorithms on top of conventional techniques. So companies like KLA Tinker, where they manufacture, where they actually manufacture devices which can fit into the manufacturing pipeline of microprocessors. There will be this huge heavy equipments, heavy microscopic imaging techniques, which generates gigabytes of data every second, which needs to be processed for understanding whether the microprocessor etching process has gone defective or not. So all these things are made possible by AI nowadays, and that is how that's how we are trying to pass over the phase of a bottleneck in uh, the manufacturing of microprocessors. So recently we are facing a lot of shortage because of the saturation of all the facilities that are out there. So when it comes to research in physical sciences as well as in engineering domain, apart from unlike the industry, there are some differences how we can adopt artificial intelligence and machine learning. So far we have been discussing the applications of AI ML in industry primarily. One thing about industry is that we only care about the output and the final product or the value addition to the business. But when it comes to physical sciences, we also need interpretable and generalizable models. So what I mean by this is when the conventional approach to model any problem that we have in any discipline of engineering or in general in physical sciences, we go about it by first of all formulating a hypothesis, then doing a mathematical model by assuming some assumptions. Then we try to formulate our problem, whether it is a process or a study of a system in a steady state or in transient conditions. And we try to solve it by imposing different conservation laws, symmetries, constraints, and solve the governing equations, and then come up with some analytics, and then study those results and tailor some engineering solutions for the problem in hand. So that is the generic procedure that we used to follow. But when it comes to application of machine learning and artificial intelligence, we actually do not know the underlying. We actually, when we try to model these things, we face the difficulty of actually interpreting how the machine learning model comes to the solution of the desired problem. So I have listed down 3 different points which actually has to be satisfied if we need to successfully employ a machine learning model in a proper physical science problem. So first of all, we need the model needs to be interpretable. So when we formulate a model, it has to have a reduced order or few terms that we can interpret how by tweaking or parameterizing different variables how the actual system behaves. So if there is a lot of nonlinearity and a lot of nonlinear terms involved and millions of degrees of freedom in the system, but even though it is giving a very good result, we may not be able to interpret and understand the underlying physics behind that. Then we need low-dimensional systems to be modeled, even when we employ AI. Why? Because if every engineering problem, even if in the case of problems that we solve or approach using numerical techniques, we have several degrees of freedom associated with that. If you are trying to solve a turbulence flow problem, when you model a domain and when you discretize or when you create a mesh, each node in the mesh has its own degrees of freedom. There will be, and based on the number of nodes, there will be like an astronomical amount of degrees of freedom in the system, which in general we cannot interpret in terms of the conventional logic that we follow from first principles. So when we apply AI, we might be able to make a reasonable model, but again the question of understanding what each dimensions in the model represent remains a challenge. And our model should be robust. It should be resilient to noise and disturbance. Like when we create an AI/ML model to predict some phenomena, we cannot go blindly about it. Even if we keep the model in a more noisy condition or in a different setting for an experiment, it should give reasonably reliable results. So these points will become clear when we take an example and try to understand things. So let me start with what is the drawback of our conventional first principle methods, and how what we can achieve with that and what we cannot achieve with it. So we know modeling in conventional methods, we can model systems with simple, linearized and idealized models. But if there are disturbances and subtle effects of different environmental variables, which are often nonlinear in nature, those cannot be accounted or captured in our simple first principle models. But with machine learning and artificial intelligence models, we can incorporate all these n degrees of freedom, all this high dimensional mathematics, but again, we cannot incorporate the non-physics in that. For instance, if we are solving a particular problem where we know from common understanding that there is we can apply certain constraints to certain degrees of freedom of the material or the system under consideration, it's very hard to incorporate that knowledge into the AI/ML model that we are trying to address. So I'm talking this in the specific context of modeling everything using a dynamical system. So every system that conventionally we talk about can be modeled as a dynamical system. Pretty much everything, not just in the mechanical engineering domain. We know a lot of things we model in mechanical engineering domain are basically dynamical system models. But even the stock market or the weather forecasting or the spread of COVID can all be modeled as dynamical systems. We just need to have the n number of variables that actually determine the state of the system, and you have to define the degrees of freedom of each of these variables. So the solution to this, to come up with the best of both worlds, so to both incorporate the knowledge from first principles and then to adopt what we have in machine learning and artificial intelligence, there is this recent modeling technique called discrepancy modeling. So what we do is we start with a partial knowledge of physics. For instance, like an idealized Hamiltonian or an idealized Lagrangian system, and then we apply whatever knowledge we have, like conservation laws or symmetries or constraints, to that particular model, and we model the nonlinear part of the disturbance part, which mostly termed as the discrepancy, using the machine learning models. So we have the input from the ideal model, which is from the knowledge of physics, and we have the discrepancy part, or the nonlinear part, the unknown effects, which are modeled from machine learning. So this was a very effective technique in modeling problems in physical sciences so far to successfully adopt AI/ML into understanding of the world around us in general, and specifically to many problems in our engineering domain. So I will first of all start with so before coming into the case studies, I would like to take you through a simple example, a pretty neat and simple example where everyone can understand like what exactly is discrepancy modeling. So we all know the Galileo's ball drop experiment. So in the 15th century or 14th century, I don't remember exactly. So Galileo first of all found the balls dropped from a certain height having equal mass will reach the ground at the same time. So the old idea, Aristotle's idea was the balls will reach at different time. But Galileo found, but through his experiments from the Leaning Tower of Pisa, the balls will reach at the same time. So in 21st century, with our current knowledge of physics, if we reiterate and think about whether Galileo was right or not, actually, what we would infer if we repeat the experiments? If we go to very small time scales and length scales and precisely measure the models, obviously Galileo may not be right. We'll find that Aristotle is right. Why? Because those are not just governed by the gravitational force. it's not an ideal condition. There are several environmental factors, like there will be the drag force of the air, or there might be a wind flowing in. The drag force may not be in this just in one direction. So there might be a shift in the trajectory because the wind is flowing in a different direction. There could be other environmental effects. Could be even though the mass is the same, if the shape of the ball is different, then obviously the drag is also different. The surface of the surface topology might also depend how the ball makes its trajectory. So there is this interesting study done by Silva and all. So they are from the Nathan Cook's lab in Washington University. So they have done. So this was published in 2020. So they repeated the Galileo's experiment for different sorts of balls, like golf ball, baseball, tennis ball. So you can see this. I'm not sure if it's visible, all these images. They took different balls of comparable masses. I mean, pair of these balls are of comparable masses, and they repeated these experiments. So here, this table actually shows you the radius, mass, density, and different physical measurements, the maximum Reynolds number of these different balls under different conditions. And they dropped it from a certain height. And as expected, we can see all these balls actually reached the ground at different time, not at the same time. So it may not be visible, this graph over here on the left bottom, but see, there are a few dotted lines over here which actually represents idealized models that we know from our knowledge of physics. The first one is a constant acceleration model, which actually deviates very much from how actually the different balls have made its trajectory. And the second one is having some kind of a drag force added to the constant acceleration model with a small viscosity term to it. But still, the model is not good enough. It's deviating from. So all these dotted models are actually deviating far off from the ideal or the actual experimental data points. So here on the right side, I have a plot where the data is again plotted in a logarithmic scale, so that things are visible more easily. So if you get the slides, you can take a look at this, or you can also go to this paper and read through that. It's very interesting study. So the idea is that the different environmental factors, like the effects due to different conditions at which the balls are dropped, or even if the same ball is dropped twice, there could be slight changes in the environmental conditions. So that could affect or create nonlinearities which are actually not accounted in the ideal models. So here they have used a machine learning technique. This is known as this technique is known as sparse identification of nonlinear dynamics. So it's nothing but a simple regression technique where they take multiple nonlinear terms for position and velocities and use them in a regression equation and try to identify the coefficients by fitting the model with a gradient descent algorithm. So interestingly, what we can find is the coefficient for constant velocity 9.8 is the strongest, but still it is very close to 9.8. It's if you read from the model, we might interpret the physics wrongly, because we might think it has the different balls have different gravitational constants at different points. Then the next strongest coefficients are coming for velocity. So in a sense, the machine learning model is actually giving an idea of the actual physics that is happening there, because the strongest correlations are happening for the constant acceleration and for the velocity. So the gravitational force as well as the drag force. Those are mostly accounted for already by the machine learning model. But then we find the small discrepancies which are actually happening at this x square term, xv term, x term. So these are not consistent, and these are small coefficients, but these are actually the non-linearities that we were talking about, which are actually arising from different environmental conditions. So while implementing machine learning models to understand the physics, because of these discrepancies, it could always be misleading. And one way to reduce this discrepancy is by increasing the amount of data, or by pumping up the number of experiments and trials, and reducing the probability of all the terms that are or the disturbances that might cancel out each other when we average it out. So this is an effective way, the sparse identification of nonlinear dynamics is a very popular technique nowadays, even implemented in multiple domains in mechanical engineering as well, to understand complex physics. But we have to be careful about how to filter out the noise and how to identify the discrepancies. Now let's start with the case study of fluid mechanics. So I now am narrowing down to my discussion in mechanical engineering. So fluid mechanics problems, we know we can always confine it into 4 different categories. So here I have listed it down. Like, so one is the reduction or reduced order modeling, where we try to find a problem with several degrees of freedom and reduce it to a space where we have a handful of variables which can be interpreted easily. Then we have the control of fluid flow problem, where in many situations where we need to control the flow through some ducts or around an object. Then we have the sensing problem, like to identify exactly where to put these sensors to measure the flow field and properties of the flow field. Then we have the closure problem, especially which we address mainly in our computational fluid dynamics simulations and others, where this if you are modeling a turbulence flow, we have the average flow field, and we have the fluctuations which can be separated out, or the fluctuating terms. And these fluctuating terms will eventually, when we model the turbulence models, we obviously end up with these fluctuating models creating non-linearities, which eventually couple these equations in a way we cannot solve it. So some of the existing solutions are RANs and LES, where we actually model this Reynolds stress using the mean flow field, or we separate out the low energy carrying vortices, but it's not an effective closure for the set of coupled equations that we have to solve to find the solution to our flow problems. So AML can again address the closure problem. I will discuss detailed about this when we come to the specific case study. Now, all these problems that we face in fluid mechanics can be reformulated or represented as hard optimization problems. So that is why we can actually implement AML techniques to address these problems. So so these are so these problems are actually even these are hard. I'm saying it is hard optimization because most of these problems are high dimensional. It has several orders of degrees of freedom. Then this has nonlinear terms coming in. Then it is non-convex. It has multiple local minima. It's not just one global minima where we can actually find a solution to the problem. And sometimes the problems are at multiple scales, like we have to find what is happening at a nanoscale, then forward the predictions to a mesoscale or derive quantities from there, and then solve the classical problems. All right. So ML is actually connected to the history of fluid mechanics. So in 1964, this Reichenberg and Schiefel used evolutionary algorithms or genetic algorithms to actually do something which is very closely can be related to what is happening in ML right now. So what they did was they conducted this experiments using corrugated plates which are aligned at different angles. They used 5 plates which are aligned at different angles, and they tried to find the optimal configuration for this place such that there is a reduced drag. And they did this using a kind of a stochastic gradient descent method. So what they did was they actually modeled the different angles randomly by using an analog random generator. So I forgot the name of this thing. Actually, the idea behind this random generator is they'll just drop a ball and it hits at one point in the bottom, and that is how they find a value which they will increment to the angle which is chosen from a normal distribution. And then this profile is generated, and finally they keep on incrementing or decrementing the values of these angles based on whether the result of experiment is a success or failure, whether the flow is actually having a reduced drag or increased drag. So, so this kind of data-driven algorithm is implemented way back in 1964. Then what happened in 1974, we all know there was this time period called AI winter where Sir Lighthill, he was this guy from a diplomat in the United Kingdom, and he came up with this a report which says there is a massive hype cycle and there is a lot of grants going into the AI research which is not delivering any results, and because of that the AI research there was no funding for AI research for a long period. It's popularly known as the AI winter. So during that time there was not much development in the field, and it's much later when we had enough developments, and recently in 2010 when people once again started applying AI/ML techniques to different problems in fluid domain as well. All right. So, to start with the case study, like how we can effectively apply AI/ML in separation of flows or flow structures, I want to first start with why machine learning is or how machine learning actually proves to be a potential candidate to target the problem of solving the flow structures in fluids. So here, if you look at the video, I hope the video is visible. I'm not sure. You can find the same video on YouTube as well. So this is Guadalupe Islands in I think it's near Japan. So it's producing the von Karman vortices. If you take a closer look, it's very much close and similar to what happens when you have a flow around a cylinder in which is simulated in, let's say, a wind turbine. I'm sorry, in a wind tunnel. So the idea behind this is when we go for large-scale flows or even flows which are happening across a mountain, there are these definitive patterns that are occurring in the fluid flow, and which can be separated at different scales. All these vortex formations can be separated at different scales. So all these patterns occur in all forms of fluid flow, and machine learning and artificial intelligence is one technique which is actually specialized in understanding and studying patterns or identifying patterns within a chaotic set of data and separating it out from the noise. So this is the reason why we can effectively apply machine learning and artificial intelligence techniques to these problems. So here is a study by Bernard Moore, and it's way back in 2003, even before all the machine learning got started. He studied this flow, the vortex shedding around this around a cylinder, and so the basic problem of vortex shedding around a cylinder is we always have this this oscillating patterns, but when we try to approach it in the conventional way, we have several degrees of freedom, and we cannot effectively solve for a solution for the problem. or effectively address or understand how exactly the flaw behaves. So he came up with this particular solution. What he did was actually very quite interesting. This is a classic work now in the field. So what he did was he actually uh, uh, transformed the coordinate axis in which the problem is represented into uh, an eigen coordinates where we have this separation of different modes. So modes means nothing but there is this concept of dynamical coordinates where or the cyclical coordinates where we can actually represent the periodic phenomenon much more effectively, like we have in the lattice waves in lattice dynamics, which can be represented in the Fourier space and the Fourier coordinates much more effectively. So just like that, we can separate out these different modes by transforming the representation into an eigenspace of the linear equations that are defining the problem. So he did that effectively back in 2003, and he actually managed to decompose these things into two different translational modes and one shift mode, as he called it. So basically what we do is we take the flow field and subtract the mean flow field, and then we do an eigenvalue decomposition, or a singular value decomposition, so it is called, and then we obtain these different modes, the so-called modes. And then after transforming the problem into this newly adopted coordinates, he was able to represent the whole dynamics using a slow manifold. So this is nothing but a simple representation in transformed coordinates for the same set of equations that represent the flow of a cylinder. And it has this vortex shading, which is actually happening only around the circumference of this conical structure. All right. So let us take a look how this can be achieved. The same thing can be achieved using machine learning. So here is a recent study, which is again published in 2016 by Steve Brunton and Nathan Kurtz. So what they did was they applied the same sparse identification of nonlinear dynamics technique to the same flow over a cylinder. So they came up with this. So it's nothing but they, to derive eventually to derive this coordinates that we have for this, or to derive the equations that we have. This that represents the flow field over a cylinder. We just have to plug in the different nonlinear terms and try to find try to fit the data of how the flow actually happens, and try to do a regression and find the coefficients for the corresponding terms and make it regress it to fit to a surface where we have an optimal representation. So if you take a look at this, here we have the three coordinates x dot, y dot, and z dot, and it is actually mapped to the different terms, the linear terms as well as the non-linear terms, and they fit the data and find out which of the terms are actually having a coefficient and which are not. And it came out quite interestingly. They managed to decompose these different terms to exactly what was obtained using the theory developed by Bernard Noack. All right. So next, we will discuss a bit about how convolutional neural network based autoencoders can do the same thing. So here we were using, so this is a pretty conventional technique. Like in terms of machine learning, there are again two types of machine learning techniques. One, the conventional stream of techniques where we do different regression models and ensemble models, which can actually model the phenomenons by fitting it into a high dimensional hypersurface. And other than that, we also have these neural networks, which are inspired by the neurons in the human brain, that can also model or learn the non-linearities within different systems. All right. So here I have. Let me just put it here. All right. So here I have presented a very simple neural network based autoencoder. It is nothing but if we feed in a complex flow field, our ultimate aim is to find those coordinates, which are nothing but those latent variables in a low dimensional space, which actually represents the dominant features in the flow. So if we look at the vortex shading, so these POD model 1, POD model 2, these are actually the dominant features in the flow, which can actually reproduce the complete flow field. So these are the eigen-decomposed repeating patterns, and we can effectively as a sum of all these different patterns, we can reproduce this flow by eliminating the effects of all the less significant or let us say fluctuating small scale patterns. So the autoencoder is also basically doing the same thing. It is actually taking an input of the flow field from a simulation data, or let us say an experimental flow field visualization, and it actually the encoder part actually scales down, or it maps through a series of matrix operations. It maps the entire flow field to a set of linear. A set of latent variables, which actually represents the dominant features, or let us say the relevant features, which we actually concern for, which is what we are actually worried for modeling the drag or the lift or whatever we are interested in. And then the decoder part takes this low frequency pieces and try to reconstruct the actual model from this few features that are narrowed down by using the encoder. All right. So this is actually taken from again from the work of Steve Brunton's group. So where they did the same kind of eigen decomposition of this flow field across a cylinder by using this POD or PCA technique, which is nothing but a fancy term for principal component analysis. It's in literature, this is commonly used interchanged with this term called proper orthogonal decomposition, but basically it means the same thing. It's simply a principal component analysis where we reduce the dimensions and or take the whole matrix and represent it in the eigenbasis. All right. So interestingly, they found so if we take, there are 1 million pixels within the simulation within this video output of the simulation of how the flow is happening. So that accounts for 1 million degrees of freedom in the flow field if we if we model it as if we model the velocity field at each and every nodes which we model for the simulation. So instead of that, here what we can do is we can subtract the mean flow field that we have here and then do a singular value decomposition and obtain these different eigenmodes. And now we just have 10. So if we are getting this 10 different eigenmodes, and if we can effectively reproduce the flow from this 10 different eigenmodes, then obviously we effectively reduced uh, the million degrees of freedom problem to a problem having just 10 degrees of freedom. And then we can go for formulating equations in this new basis to obtain something very similar to what is achieved by the study of Bernard Novak and others. All right. So here is the famous homogro scale, which actually represents the scale separation of different coherent flow structures and eddies. Everyone who has been studying turbulence, it's a pretty familiar figure for you. So we have these different regions where we have large eddies where most of the energy is contained. Then we have the scale separation between small structures when we come to the right. So basically the x-axis represents actually the frequency, the spatial frequency, which is nothing but the spatial wave vectors of these different features that we are having. And when it comes to modeling this different flow problems, or to identify the lift and drag, or to design for an engineering solution, we obviously want to solve for the large eddies which we are majorly concerned about. So let us take a look how machine learning can actually help us in addressing this closure problem. So where we have this small flow structures which we effectively need to we can neglect, but we are unable to neglect it because the effect of the variables representing those are actually coupled into the equations of the large eddies. So we can neglect the effect of the small eddies, but we need to account the collective effect of the small eddies, how it correlates with the large eddies. So this problem once again is well studied and is actually got a lot of attention in the AML based community. And what we do is, in fact, we come up with a solution where we have this machine learning models where we can actually impart partial knowledge of physics to solve for the final output. For instance, here Liang and Templeton has come up with a technique where they have this conventional neural network model, and on top of that they have an additional tensor input layer where they can input some rotational invariances to actually control and actually impose the constraints of conservation laws into the model, and make sure that the actual model obeys the classical physics, as well as at the same time accounting for all the non-linearities from the smaller fluctuations that are happening within the flow field. I hope that is clear. Not sure if. Okay. Anyway, we will come back to this one. All right. So another area where machine learning models are effectively applied is in reconstruction of flow field. So here we have some sensor measurements which are actually made only at few points and not the entire flow structure, and we can effectively reproduce the complete flow field even with sparse sensor data by using a neural network. So this neural network is again trained in a lot of machine learning, a lot of turbulence data, which is nowadays plenty of turbulence data and simulation data especially is available in a lot of open source repositories like the John Hopkins Turbulence repository and many others. So we only need to collect experimental data in sufficient quantity, and we can effectively reproduce and predict the flaw fields. So this is one area where a lot of research is happening. So the reconstruction of flaw field again can happen. I mean, we can do that in two ways. So either it could be making up the flaw fields which are actually having missing information as the time elapses. So for such cases, for the interpolation of the flaw field or the missing information in between the missing timestamps, what we can do is we can train the models using intermediate data from intermediate timestamps. So this is what Erickson and others have done in this work. This was also published recently in 2020. And there are also scenarios where we want to predict the future flaw field. This is not as effective. So this is like extrapolating the flaw field in the future. So in that case, what we do is we actually train the whole model using all the previous data available to the timestamp up to that point. This is mostly done with recurrent neural networks, and then we try to extrapolate it to the future. But this extrapolation is not as effective as the interpolation. As we can see here in this figure, there is serious degradation to the figure at the right when the timestamp has gone to 50. But this technique is also adopted and is currently used in weather prediction and weather forecasting and all that. And people are predicting successfully up to months, weeks, and months. All right. There is another this interesting study by Siddharth Verma and others where they used deep neural networks to actually understand how two different fish is actually making an effective or an efficient swimming pattern within a still water body. So this simulation actually is heavily driven by data, and they conducted this with massive power grid computing from a community grid. And you can check this paper out if you are interested in. I have also not explored it that much, but it's quite an interesting study. So these are these are the things currently going on in fluid mechanics. Then when it comes to manufacturing, we know additive manufacturing is the new disruptive technology, and there are primarily three different sub-classifications where AIML is actively employed nowadays. So it's again from this review paper from Wang and all. So they reported that AIML is actively used in power bed fusion, direct energy decomposition, and material extrusion. But in general, there are a lot of processes in every stage of additive manufacturing. There are many different places where AIML is actively employed. So, for example, in material design, in topology design, then in power spreading characterization during the process stage, then the process optimization, and finally in the production stage also, in manufacturing planning, quality control, and all that, we use different types of AIML techniques. So I have taken a few studies which are related to material discovery and topology design, just to give a brief overview. So here in material discovery, we know the number of possible materials that we can synthesize nowadays based on the elements that we know today is like 2 to the power 100 or somewhere around that sort of number. So it's not possible to actually narrow down and study, follow the regular process of synthesizing all these materials and studying the properties and trying to find out what is the ideal material for a specific use case in the industry. So AIML has come handy in this kind of scenarios where we can Actually, so here there is an example from again another study from Wang and all. So where they have optimized this microstructure lattice to design a material of a much better thickness and much lesser weight. So this is completely done using neural networks. Then when it comes to topology design, once again the conventional topology optimization techniques, they are pretty compute intensive, and here we have found that generative adversarial networks or GANs are actually coming up with um, much better solutions. So GANs can basically generate a lot of new structures with given inputs by keeping the constraints and satisfying the system design conditions. They can generate in number of different structures that we may not even know about beforehand. So this has now been actively employed in topology optimization and topology design of different mechanical parts. Now, when it comes to material science, we have machine learning actively employed in the design of potential force fields to model the materials. We know especially in biotechnology or in organic chemistry, if we need to model different materials, or whether it comes to non-organic polymers or maybe crystals, modeling of crystals, all we depend upon heavily upon different force fields that are developed from ab initio or quantum mechanical calculations. But these calculations are pretty compute intensive, and we cannot study large scale systems. Mostly this is done using molecular mechanics, molecular dynamics, or ab initio techniques like density functional theory and others. But the machine learning potentials are now making a paradigm shift in how we approach these problems. So the advantage of machine learning potentials is we are actually able to achieve the accuracy of quantum mechanical calculations. At the same time, they are way faster, and we are able to do the simulations and taking it to much larger length scales and time scales, which is not previously possible because of computational limitations. All right. So and when it comes to classical scales also, if we need to do multi-scale modeling, there also we can bridge the gap between molecular scale modeling and classical scale modeling with coarse-grained machine learning potentials and force fields. All right. So here I have given. So there are also some challenges in material science when we come to how we model and represent materials, because mostly when it comes to materials modeling, it's all about how we represent the materials. I mean, represent the system and model the system in a mathematically efficient way. Because obviously the size of the system, or if the number of molecules or atoms are different, then the number of degrees of the freedom of the system is again different. And when we try to train a model for one system with a specific size, the state vectors are representing the system. If it is having a different size, it cannot be fed into a new machine learning model. Or if we are taking a different system of a different size, it cannot go into the same model and give us predictions. So here there is another. So there is a solution actually proposed recently by Baylor and I forgot the name of the other guy. So these two guys have done a lot of work in this domain, and they came up with the solution of actually using independent neural networks for each isolated environments around different molecules. So each molecule can be represented using some sort of generalized symmetry functions, which actually formulates the environment around the molecules, and then we feed it into a neural network, and that will give us the final predictions. All right. So now I would like to touch upon briefly on nanoscale heat transport as well. So because classical heat transport obviously don't have much applications in machine learning. So but when it comes to nanoscale heat transport, this is again something which was also explored in our lab, in our group. So we have these systems. So this the figure you see here is nothing but a graphene nanochannel with water flowing in between. So here we have the problem of thermal boundary resistance. It's a nanoscale phenomenon. Like it becomes relevant only in scales in scales less than 1 nanometer. Because in classical scales we obviously have the contact resistance, which is way much higher compared to the thermal boundary resistance or the so-called Kapitsa resistance. This kind of resistance actually arises even at a perfectly smooth interface, even with perfect contacts. And when it comes to nanoscale solid-liquid interfaces, we have this problem of formulating the Kapitsa resistance and how it behaves across the interface. We know the heat carriers in solids and liquids are quite different. In solids, it's obviously the quantized lattice vibrations of phonons and electrons, and mostly in case of graphene over here we can neglect the effect of electrons because it's a semiconductor without much valence electrons. But when it comes to water, it's mostly the molecules, the diffusion of molecules that will carry the energy. But in nanoscale interfaces, there are different phenomena happening, like liquid structuring, which makes the liquid actually behave like a semi-solid. And we have this liquid structures actually supports some shear waves other than pressure waves, and behaves like a semi-solid. And above the Frankel frequency, it actually supports these shear waves or this density waves, which actually have behave like quantized phonons or vibrational carriers. So to model this kind of phenomenon, once again, it is pretty difficult with the conventional approach. We can the existing theories like acoustic mismatch, diffuse mismatch, etc., will give you a few orders of magnitude higher values compared to the experimental reports. So we have attempted this thing using molecular dynamics, and molecular dynamics actually quite effectively reproduce the results that we have obtained in experiments. So in molecular dynamics, we use the theory of generalized hydrodynamics, where we combine it acts as it can act as a bridge between both laboratory experiments and the theory. So if you take a look at the flow physics in nanoscale fluid systems, all the structural, thermodynamic, and transport properties can be effectively represented or derived in terms of time correlation functions from the theories of molecular hydrodynamics. So, but in most of the cases, just like in case of Kapitsa resistance, where it's very difficult to reproduce the actual experimental conditions because of the necessity of highly polished and smooth interfaces at nanoscale. Sometimes we can actually validate this theory using the computer simulations or molecular dynamics simulations. And in case of absence of sufficient theory, we can validate the laboratory experiments directly with computer simulations. So molecular dynamics actually props this regime of the length scales and time scales, where neutron scattering experiments are conducted. So mostly it is around 10 to the power minus 8 Armstrongs in length scales, which is the length scale of atomic collisions and in free path of atoms, and time scales also in 10 to the power minus 13 seconds. So basically, this compensate each other. But again, when it comes to molecular dynamic simulations, these are pretty compute intensive. So we even though we can effectively reproduce the Kapitsa resistance using molecular dynamic simulations, we we actually need to run heavy computer simulations, which takes days or even weeks and months to come to solutions. So here we tried to solve in our lab. We actually have solved this problem using machine learning. So here in this figure, I'm not sure if it is very much visible. You can see some stars and some circles. So the circles are actually the figures produced from uh, molecular dynamics, and the stars are the figures, the data points produced from machine learning. So this machine learning models are run after training this on the simulation data. This will run in just few seconds. So you can see we have this is two different parameterization for temperature and I'm sorry, for pressure and contact angle for the same study of thermal boundary resistance or Kapitsa resistance. And you can see machine learning has produced almost, produced very accurate results close to molecular dynamic simulations, which were obtained by running simulations for more than a month. So this machine learning models predicted to near good accuracy in just about a few minutes, a couple of minutes. Uh, and here, if you observe closely, we have actually tried out different models. Like the first one is a linear regression model in a high dimensional space by taking all considering all the different descriptors that actually characterize that nanoscale interface. Second one is nothing but a kernel-based model called a support vector regressor, and it's based on a non-linear basis function called the radial basis function. And the third one is a decision tree based model called, it's an ensemble model. Actually, it's a gradient boost ensemble, which is a collection of decision trees, which is boosted for performance. All right. So here is a comparison of again a comparison of the best performing models that we got. So we found that compared to molecular dynamics, machine learning actually predicted the Kapitsa resistance up to 92% accuracy. Like the gradient boost model was giving the best accuracy, it actually gave a 92% accuracy in prediction of Kapitsa resistance. We have some theories and some empirical correlations from literature which actually came up to 64% accuracy. That was the best work in based on a seminar work which was done in 2016 by the Kamutaskos group. But we managed to improve that by almost 30% by using machine learning techniques. All right. Hope that's all I wanted to cover as part of the discussion. If you have any questions, I will be happy to address them right now. Please feel free to ask anything. Because I cooked this presentation up in just 2 days, I had some struggle. I never gone through the slides any time before, so I was having some struggle explaining things. So that doesn't make them. But if you have any questions, I will try to address them and explain things more clearly. I hope. Hope I'm audible. Am I audible? All right. So, anyone has any questions regarding any of the topics that we discussed? So, if so, you can just raise your questions, or you can unmute and just ask me. hope nobody has any questions. I actually planned a hands-on demo on how to do the Cindy analysis, but unfortunately, I think I can do that hands-on demo if you need. I don't have the data with me right now because I connected from a different system. But I can show you some demo how to go about it, and then later give you directions like how to find uh, the, the right kind of approach to go about it. Uh, Oh, can anyone speak up? Because I'm afraid I'm not audible, or maybe there is no feedback coming from your end. So I'm not sure if I'm still just presenting by involving myself.
Yes, sir. You're very well audible.
Oh, okay. Thank you so much. Okay. So are there no questions like was the presentation not like, I mean, couldn't understand it, or could you get an overall idea about things, what is going on right now?
Yes, sir. The presentation was very well.
All right. Okay.
Are you planning to give some hands-on sessions? Or?
Yes. So that's what I was thinking. Actually, I thought maybe I could do a hands-on session. Uh, so up to what time we have? Like how much time we have? I would like
So we
to
have time till 9.
check out that also. Okay. All right. All right. So right. So what I'll try to do is I will just. Okay, so what I will do is I will just give you a hands-on demo on how to build some of these models, because we may not have enough time to build something like um, a Cindy model, or maybe a encoder decoder network. But I will just give you an overview of what are the different tools that we are using. So I usually work with uh, mostly, we work with high-level APIs, Python-based APIs, mostly available from different libraries like scikit-learn, TensorFlow, Keras, PyTorch, etc. Uh, so here, to get started with, first of all, I will switch to a suitable Python environment, and to get started. So sometimes when we implement our own algorithms, which when we tweak some of the existing machine learning algorithms, for instance, when we try to implement uh, uh, this kind of uh, uh, tensor input layers into an existing neural network model or something, then we have to go into a much low-level implementation. We might be tweaking some functions inside TensorFlow, or writing some CPP libraries using routines like 2DMM or something. So that's what we do mostly in our lab. But anyway, let me give a simple demonstration of how we can go about this. So first of all, Python environments, again, you can go develop different environments so that you can isolate different projects which will not conflict on dependencies with each other. So I will shift to an environment here. I have an environment. Sorry. All right. So I'm in a Python environment right now. Now I will. I don't know how many of you are familiar with Python. So We can also do this in just about any other language. But Python is the most popular and most widely adopted one nowadays. Um, and another one, obviously, having a lot of CPP, a lot of machine learning libraries is uh, uh, C++. So let me just open one notebook. All right. So first of all, okay. So I thought of okay. Let me do a simple. Let me demonstrate a simple uh, how to build a simple model using the Keras API, a neural network model using Keras API, and um, then I will take you through uh, uh, how you can actually solve models in uh, let us say a particular problem that that you want to solve, where you can get the material and where you can get started. So first of all, I will let me just import the TensorFlow. Oh, I hope I'm using the right commands. So So I am importing this TensorFlow library from Python. So I have the version 2.82. So this is what I am going to use for my modeling. So I import another library called random, and I will just create a random seed view for reproducibility. All right. Another thing I want to do is, oh, sorry. Uh, all right. Uh, Maybe I can import. Okay, so let me do this because of time constraints and I don't have any data. So what I will do is I will just use one of the data's inbuilt data that is available in TensorFlow libraries. So I believe it is in data sets. We have, let us say, we can import list. All right. So what I'm going to do is I will just demonstrate how to create a simple neural network. So let's
Hi,
get this data. Yes, sir.
actually, the participants are putting comments like screen is blurred and they couldn't see it.
Oh, all right, okay. But I don't know what we can do about
I
that
think Abhijit,
because.
you can if you can share the codes, that would be great.
All right, but all right, okay. So okay, I can tell you where to find code. Then we don't have to download this. I mean, have to go about it line by line. So maybe I will tell you some places where I can find example codes. So there is this GitHub repository by Dynamics Lab. They have some excellent material to get started on mechanical engineering and flow problems. Dynamics. If you search for Dynamics Lab GitHub, you can go directly here. Yeah, so just take a look at these repositories, and I will show you how to access these different. They have both data and notebooks. So let us
Yeah.
say we want to take a look at. Uh, hmm,
Abhijit, can you share
this.
that link to the
Yeah.
chat box?
Yeah. Sure. Okay. So let us say we want to see how. Uh, looking for some simple problems actually. Data. Okay. Okay. So let us say we have to go through this. This modified syncing. All right. Okay. We have some notebooks. No, these are not notebooks. Okay, this one is notebook. So we have this Langevin regression. Data book type, notice data book type. You look at the whole collection of repositories available. Okay, deep learning fluids. So we have this deep learning fluids repository. They have some few notebooks here. Some tutorials. See, advection diffusion equation solved using deep learning. Lawrence time step. Don't know what that is. We can check this out. So suppose if you want to check this particular repository, what you need to do is you just have to. I'm sorry. You just have to come to this repository, get the GitHub link over here. You can just copy this thing, and you can come to your terminal, whatever you're using, and we can just go on this thing. Okay. So I think I have a directory with the same name over here. So deep learning fluids. All right. So I have this repository here. So I can open my Jupyter notebook. This one. See, now I got all the codes from GitHub right here. So now I can directly open my problem over here, my notebook over here. And then you can try running these things, these different cells, and see what is happening. So all the code and the description, what each cell is doing, it's all given over here. So it's a pretty detailed tutorial. So you can just go through this and generate the output from different code cells and see how this works. It's pretty self-explanatory. I just wanted to show you, explain a few commands that are related to deep learning. So here we are actually using two different libraries. So one is mostly in research arena we usually use a library called PyTorch, but these libraries like TensorFlow and Keras are mostly used in industrial applications. So TensorFlow is like mostly for tensor operations. You can perform any sort of tensor operations, and if you need more fine-grained control over your models, you can do it using TensorFlow. And Keras is now fully integrated into TensorFlow. It's like more of an abstraction on top of the original TensorFlow library, and it gives you much high-level APIs which you can use to model your systems if you don't need much fine-grained control over your algorithms, and if you only need to use the built-in subroutines that is available within TensorFlow. So it's training a model with Keras is pretty straightforward. So here what we are doing is we are actually importing all the libraries. So next, let us see. We are trying to solve the advection diffusion equation over here. I'm sorry. All right. First of all, we will solve it using the conventional numerical technique by discretizing the equation. And then using a numerical technique to actually find the solution. So you can go over the code. So this discretization part, and it's pretty much simple like your finite element and CFD techniques. And we are plotting the solution. So we are getting u as a function of x and t. So it's a simple it's a pretty simple straightforward problem. Then once you have that, okay, this is the part I wanted to explain. Uh, when it comes to machine learning, so what we do is we actually uh, take this input. So here we generate this data or this data points. Uh, uh, I believe we are doing it. Yeah. So here we generate the data points actually from uh, some functions that we define as part of this. Uh, yeah. So we are not importing any data. So we are generating this data right here itself. So we are inputting that data right away here into these arrays, and we are splitting it into a training set and testing set. And once we obtain this data, we see here is the part where we actually create our model. So creating the model is pretty much simple. Like we call this keras function called tensorflow.model.sequential. I don't know why this is. Okay, all right. Then we keep on adding the different hidden layers in the model. So here I am adding one densely connected, two densely connected layers with activations ReLU, and the final layer activation is linear. Uh, so activation functions are nothing but so basically this neural networks are nothing but matrix operations with some nonlinear activation functions which are coming in between. Uh, so basically these activation functions are meant to switch the neurons on or off, or it will ideally it will push your final output from that particular neuron to 1 or 0. So densely connected means every neuron in the previous layer is actually connected to every neuron in the other layer. So it's like so here we are creating a very simple model. We also have more complex models where we will have in between these different layers we will keep on adding dropout layers and normalization layers, batch normalization layers, and such things. And we have very deep models. And sometimes if we may not build our whole model from the scratch, sometimes there is this concept of transfer learning, where we take an already existing model which is well trained on data, and we only train a few layers, few selected layers to the bottom of the model, which actually needs to be retrained. And then we compile this model with a certain loss function, which actually computes the total loss and backpropagates during each iteration. And that is how we optimize the weights during the simulation process. Then we have this command which is actually fitting the training data to the model. So here this function so basically takes the training data, the input variables as well as the training output, and it actually conducts this in batches. Like the whole training data will not go at once. One batch will have 32 inputs which are going at once. So these different functional parameters you have to pass in every time when you are defining a model. Epochs means nothing but the number of iterations that we are having over here. So we go through 10 passes for so in each pass we have 14,918 batches which are going in, and the size of each batch is 32. So that is the whole idea here. Then we have a validation data. So if we give the validation data here, it will keep on calculating not just the loss from the training data, but also the validation loss. So how best we are getting it. Then we have this callback function for early stopping, and there's something called as patience. So it's nothing but the callback function is nothing but if it's a criterion for when to stop. If we are not having much difference between consecutive values in 5 iterations, then there is no point in going for all the 10 epochs and we can stop in an early stage. Here it's just 10 epochs, but usually when we do a fluid simulation, it could be 1000 epochs. So we obviously need a robust callback function to terminate the simulation once it has converged. So this is our model. Like, it's a very simple model, just 3 layers and very few parameters. But this is not the usual scenario. Like the encoder decoder models, networks that I demonstrated during the presentation, those will be having like hundreds of thousands of parameters. So there we are using, so these are simple neural networks. So the convolutional neural network concept is slightly different. There we have this feature weights, which actually, or the feature maps, which actually is slid across the entire matrix that we are trying to narrow down. And here, so those feature maps are constitutes the weights in case of a convolutional neural networks. So and it will not be densely connected, or each neuron in each layer will not be connected to each neuron in the next layer. So that's the difference between CNN and a normal neural network. Then finally, we are having some metrics for estimating how much is the training loss and how much is the validation loss. So it seems that the training data has fit well, but we have much better validation loss, much higher validation loss, which is obviously expected because there is some overfitting in the training data. It always happens to some extent because the noise or the high frequency features which is not expected to be learned will always be there. Then here, so this is another library called Seaborn, which we can make use of. It's effective in plotting and making quick plots. Again, it's a high-level API. We will not have much control over things. If you need fine-grained control, you will have to use something like Matplotlib. All right, I believe Seaborn installed in this one. Okay, so this is just the plotting part. I am not going deep into this, like it's self-explanatory. Okay, so again, we are doing an approximate integration using recurrent neural networks here. So recurrent neural networks are again something which we haven't discussed, but when it comes to data with timestamps or time series data, we obviously cannot go for the conventional convolutional neural networks because it cannot have any correlation between data which is coming from the previous timestamp. So recurrent neural networks actually have this cross connection between or information passing between previous timestamps and future timestamps, and it makes the prediction by taking the inputs from the current layer as well as the previous layers, and then try to predict the final output. All right, so here is an implementation. I'm not quite sure how familiar you are with recurrent neural networks. So, but the procedure for developing or building the model is pretty much similar in Keras. You just need to call the same APIs, Keras model sequential, and then keep adding the layers that you need, and finally compile the models with the appropriate loss function and choose an optimizer for your gradient descent algorithm. Then we fit the data to the model that we selected, and finally we obtain the outputs. So this is the same procedure. It's nothing different. So if you take a look at it, pretty much similar for whatever we have done. I mean, whether it is for a simple neural network or whether it is for a convolutional neural network or for a recurrent neural network, it's not, the Keras interface is pretty much similar, and most of the functions are almost similar. So you can repeat the same steps and build these different models. I would say that you just give it a try. I mean, it's very difficult to convey all these things in such a short span of time. Um, but you can go through the documentation and always give it a try, because you don't need to know the nitty-gritties or the math behind how the algorithms are working to actually try out these different functions. You can just give the input and see how the predictions are happening for different outputs. So these are again some plotting functions, which is pretty straightforward. With basic knowledge in Python, we can actually make excellent plots. So that is all about how you do machine learning using Python. So when it comes to even low-level APIs, like when we do it using for better performance, when we do it using a CUDA kernel, or when we write some kernels for parallel computing, it will be a little more involved, and we will need to write the algorithms in a little more detailed fashion. But when it comes to simple problems that like we discussed today, we can always follow this approach. You can take these kind of notebooks that are already publicly available in GitHub or any other platforms, and just get started with what is already there, and build your models on top of this, like which defining your problem first, and identifying the right input features, and then plugging it into the models and tweaking your models to fine tune the final results, and then arrive at the conclusions that you need. So I hope, yeah, that's how this works. Yeah. Anyone have any questions? Or,
Yeah, Abhijit,
yes, sir.
I have a doubt.
Sure, sir.
Hello. Yeah.
Yes,
Like
yes, sir. Yes, sir.
we are very rarely dealing with mechanical engineering problems, but most of the time when it look into different problems, the availability of data uh,
Mhm.
related to large structures and all a problem. So one solution heard is like we can simulate the structures and simulate the problem, and we can get the data from that.
All
So,
right.
in your opinion, how reliable it is to take data from simulations for
Yes.
machine learning?
All right, I got it. So that's a very good question. If you are asking about, so it again depends on the scale at which you are simulating the problem. Let us say you are simulating the problem for computational fluid dynamics. Then we have a plethora of uh, uh, data which is already available, like I would say, like data centers full of data which is already available by um, researchers who actually did simulations, and which is stored in different university repositories. So these things can be exploited. These are very well simulated data sets, and the simulations are quite reliable. Uh, but if you are talking about mesoscale phenomenon, or when it comes to nanoscale phenomenon, we mostly do simulations either, or we pretty much model things. Let us say in a microscale case, we actually model things using a Boltzmann transport equation instead of solving for the Navier-Stokes or for the energy equation, for that matter. So in that case, again, there are some discrepancies. There are several assumptions that we take, and the data may not be that reliable as in case of classical scale. There are more disturbances in the data, and it is not always a feasible solution to rely upon data, but still the data is much more reliable. But if you're talking about again pure nanoscale simulations, which are purely driven by classical molecular force fields, and which are modeled using the Hamiltonian mechanics, then such simulations are not much reliable, in my opinion. Because primarily because these force fields are basically not an actual representation of the systems. It's basically tuned to study just one property or the other, and people have adopted this in studying numerous. I mean, the force fields that are optimized by one group might be taken by other research groups and studied in a number of different cases before even validating the basic, whether the basic thermodynamic state or the equation of state is satisfied or not. So such data, there is also a plethora of data available from molecular dynamics simulations and Monte Carlo simulations. Monte Carlo is a little more reliable in that sense, because all the different ensemble states are actually modeled using uh, actually randomly modeled. So in molecular dynamics, there is this danger of breaking the ergodic hypothesis, where you have repeated. When you take the time average, the system might be already going in a periodic fashion, and it may not be covering all the ensemble states. But Monte Carlo actually clears that problem. So Monte Carlo data is little more reliable. And when it comes to DFT, or you're coming to the quantum level and you're doing collecting data from ab initio simulations like ab initio molecular dynamics, or maybe density functional theory, or like first principle related calculation, they are little more reliable in that sense, in the sense that they are much closer to the theory, and uh, we have so many instances where this is matched with experiments and we have got accurate results. But again, those data are not available in large volumes, that people are actually using such data to fit different machine learning potentials. But the data is quite reliable. I mean, the potentials that are developed can effectively reproduce many phenomena. For example, I recently read this paper where they have studied the intercalation happening in lithium-ion batteries, and the ionic liquids forming intercalated layers near the cathode interface. They successfully simulated the chemistry, the reaction chemistry at that interface using this machine learned potentials, which are actually learned from the ab initio simulations. So that's also possible. I mean, to some extent, I mean, the data is reliable, but in between this from the mesoscale simulations to the molecular simulations, where we make a lot of approximations, lot of classical approximations, it may not be reliable, because when it comes to nanoscale, obviously the quantum effects and the size effects are coming into picture, and those disrupts the simulations, and in most cases our reduced order models will not be reliable. But obviously in the quantum scale, where we use the proper first principle techniques, and also in the classical scale, where we solve for RANs, where we go for RANs or Elias simulation data, they are much more reliable and much more comparable to experiments. There are some actually some very good data sets. If you, I think I already mentioned about this John Hopkins turbulence data set. They have like simulations of massive flows, massive turbulence flow with several coherent structures that several coherent flow structures that form at different Reynolds numbers. And this data has several patterns that cannot be extracted by any non-analytical methods that we follow right now. So there are a lot of groups working in this area who are actually trying to make sense out of these patterns, because if we properly decouple the different eddies over there and understand the mechanics, and using some control theory, if we can manipulate those, we can achieve excellent drag or lift or efficiency or whatever we need in a lot of scenarios that are currently of interest in the industry. So obviously that data is much reliable, and if you are interested, you should definitely go for it.
Okay.
Yeah, so that is my take on it. Yeah.
Okay. Thank you, Abhijit. Okay. From the participant side, is there any doubts to ask? You can ask. Yeah, I think there's no doubts from the participant side. So thank you, Abhijit. I think we can wind up the session.
Sure.
Actually, it's a 2 hour full power pack presentation. Like, you have covered a lot of things, from starting from basic machine learning to so many different application areas in mechanical engineering. So it will be helpful for our participants, I think. So thank you, Abhijit.
Yeah, thank you very much, sir. Most
Yeah.
welcome.
Okay, so participants, so we have completed our online session today. So starting from Monday, we are having the offline session, full hands-on session. So kindly attend complete sessions. There will be 5 days, and it is very important to have the hands-on sessions. Okay. So thank you all. See you on Monday then at Department of Computer Science, QSAT. Thank you, Abhijit, once again for accepting our invitation and delivering such a wonderful talk.
Most welcome, sir. Most welcome. Yeah.
Participants, the the week one assessment link will be shared now. Kindly fill in by 10 p.m.
Okay, good night all. We can close the meeting.